CrEn3 FeCl4 taken 3 times. So it is like LiPO4 LiPO4 Li plus PO4 carry 3 minus. So therefore 3 Li plus ions. But here 3 anions are present. So therefore you can treat it as AlCl3. So AlCl3 consists of Al3 plus and 3 Cl minus ions. So therefore if you ionize this, we will get CrEn taken 3 times 3 plus. This is cation present in the salt. FeCl4 and this will carry -1 charge. So these are the cations and anion present in the complex. Now chromium oxidation state is X. Ethylene diamine, so it is a bidentate ligand and neutral ligand, so it is equal to +3, so X equal to +3, so therefore oxidation state of chromium is +3. See, En is bidentate ligand, so each ethylene diamine donates its electron pair to the 2 electron pairs to the empty orbitals of chromium ion. Therefore, chromium ion in this complex accepts totally 6 electron pairs from 3 ethylene diamine ligands. Now, in case of iron, here X plus 4 minus 1 is equal to -1. So X equal to +3. So oxidation state of iron is also +3 here, remember. And in case of anion, metal name changes as ferrate. Now first write down the cation name. While writing the cation name, remember that first ligands. So it is tris. 1,2 diaminoethane amino diaminoethane, keep it in brackets. Next, chromium, oxidation state 3. Next, anion, again ligands first, tetrachlorido ferrate, oxidation state of iron is +3, therefore it is the name of the complex. Tris 1,2 diaminoethane chromium 3 tetrachlorido ferrate 3. PT, PY taken 4 times, PTCl 4 times. Now, PY is abbreviation for pyridine. Pyridine C5H5N. What is its structure? Hexagonal ring structure, heterocyclic compound, nitrogen atom is there. So this is pyridine, neutral ligand. So each pyridine donates one electron pair. So therefore it is a monodentate ligand. 4 coordination number, because platinum is accepting 4 electron pairs from 4 pyridine ligands. And anion complex, platinum is the transition metal ion and 4 chloride ions are present in the complex. So therefore coordination number of both the platinum metals in both cation and anion complex is same, 4 coordination number. And we have to check the oxidation state. Platinum, already I told you, it may exhibit either +2 or +4. So if you take plot Cl as -1, -4, so if platinum exhibits +2, then its charge will be -2. So here pyridine is 0, 4 ligands are there and 4 into 0, 0 only. So therefore, to neutralize this anion complex, it should carry +2, complex ion carry +2 charge. Now, in both the complexes, oxidation state of platinum is 2 only. So, treating pyridine as a complex ligand, name starts with tetrakis. Tetrakis, pyridine, platinum, Roman number 2, oxidation state +2. Next, tetrachlorido platinate, because it is anion complex. Platinate, Roman number 2, because in both the complexes platinum is the transition metal ion having +2 oxidation state. Clear? Now, almost all varieties of complexes I discussed. Now, you suppose in coordination chemistry chapter in NCERT textbook, if any exercise is there, so try to write their IUPAC names of coordination compounds, because IUPAC names of coordination complexes important, because in Neet examination they may give direct question on the IUPAC, or like organic compounds, coordination compounds also exhibit isomerism. So the isomers of coordination compounds are classified into 2 types, like in the organic chemistry: structural isomers and stereoisomers. Coming to structural isomers, these are different from organic chemistry, organic compounds. And in case of stereoisomers, like organic compounds, cis trans isomerism, that is geometrical isomerism, and optical isomerism. So coordination compounds also exhibit both the type of isomerism. So in case of entrance examination, they may give 2 compounds IUPAC names, and they may ask what type of isomerism present in that compound. For example, they give 4 IUPAC names of the compounds, and then they may ask which one of the following compound exhibit optical isomerism. So therefore, while attempting the question on structural isomers or stereoisomers, must be familiar with IUPAC nomenclature. Suppose if they ask on valence bond theory, hybridization, magnetic properties, whatever it may be, if you are familiar with IUPAC names of coordination compounds, then only you can able to attempt the question on valence bond theory or crystal field theory, Werner's coordination theory, or isomerism. So therefore, it is most important part of coordination chemistry. Now, theories of coordination compounds. Here, coordination theories. These theories proposed to explain the nature of bonding, properties of coordination compounds, nature of bonding in coordination compounds, and properties of coordination compounds. Once upon a time, 100 years back, if you see a double salt like KCl, MgCl2, 6H2O, this compound gives identification test for K plus ion, Cl minus ion, Mg2 plus ions. So that means if case carnallite is dissolved in water, so the aqueous solution responds to identification of K plus, identification test for Cl minus, identification test for Mg2 plus. In the same manner, the salt with 4 moles of KCN and 1 mole of FeCN taken twice. So they thought that this is also a double salt like carnallite, but if this salt is dissolved in water, aqueous solution we will get. That aqueous solution gives identification test for K plus ion, but failed to give identification test for Fe2 plus ion and failed to give identification test for Cn minus ion. So even Fe2 plus ions, Cn minus ions, both are present in the solution, both are present in the compound, but the solution does not respond to identification test for Fe2 plus ion and Cn minus ion. So these type of compounds, like some of the ions lose their identity in the aqueous solution, those compounds the scientists named as complex compounds, because they didn't understand the nature of bonding and the properties of these compounds. So that is why these are called and they are called them as complex compounds. First time in beginning of 20th century, name Werner tried to explain the nature of the coordination compounds, and he prepared cobalt 3 chloride complexes with ammonia, and from the observations of cobalt 3 chloride complexes with ammonia, he proposed a theory called Werner's coordination theory. The name of the theory, Werner's coordination theory. He proposed that theory at the age of 26 years only. So the first person, maybe he is the youngest person who received Nobel Prize for his complex compounds theory of coordination compounds. Okay. Now, before going to explain Werner's coordination theory, first what he did. See, He took COCl3 solution, cobalt 3 chloride solution. CO is cobalt, not carbon monoxide. Okay. Now, through ammonia gas is passed into the solution with different ratios. So here you treat it as 1:6 moles like this. COCl3, 5NH3, COCl3, 4NH3, COCl3, 3NH3. So with different mole ratios, he prepared 4 compounds. So this is called hexamine cobalt 3 chloride. This is pentamine cobalt 3 chloride. This is tetramine cobalt 3 chloride and triamine cobalt 3 chloride. So after passing ammonia gas into cobalt chloride solution and the solution is crystallized, again he took crystals of COCl3, 6NH3. Remember, solid state. He dissolved in water. See, first COCl3 solution is there. Ammonia gas is passed in various proportions and he got about 4 types of compounds. He named them as hexamine cobalt 3 chloride, pentamine cobalt 3 chloride, tetramine cobalt 3 chloride, triamine cobalt 3 chloride. So he prepared 4 different types of cobalt 3 chloride with varying compositions of ammonia. Understood this? After this, all these solutions are crystallized by evaporating the solution. So he got cobalt 3 chloride, hexamine means hexamine cobalt 3 chloride. So remember that hexamine cobalt 3 chloride, pentamine cobalt 3 chloride, tetramine cobalt 3 chloride, triamine cobalt 3 chloride. They have different colors. They are different. Now see, first hexamine cobalt 3 chloride is dissolved in water. So aqueous solution is formed. So treat this as 1 mole of the compound and 1 mole salt is present in the aqueous solution, and this solution is treated with, very important, excess of AgNO3 solution. Excess, large excess, with excess of AgNO3 solution, and he got AgCl precipitate. AgCl is precipitated, and from gravimetric experiments, and he got 3 moles of AgCl precipitate here. Now see, COCl3, 5NH3 crystals, solid, dissolved in water. So aqueous solution is formed. Again the aqueous solution is treated with excess of AgNO3 and AgCl is precipitated, and if it is 1 mole of the salt, then he got 2 moles of silver chloride. Next, COCl3, 4NH3. This solid 1 mole, let us suppose that this is dissolved in water, aqueous solution is formed, and this aqueous solution is treated with large excess of AgNO3 solution, AgCl is precipitated. He estimated it as exactly 1 mole. Now, lastly, last compound COCl3, 3NH3. This is dissolved in water. So simply salt is dissolved in water, thereby aqueous solution is formed. If this aqueous solution is treated with excess of AgNO3 solution, no precipitate is formed. So from these experiments, he proposed theory to explain the coordination compounds. So he just conducted experiments only on cobalt 3 chloride ammonia complexes and proposed a theory which is called Werner's coordination theory